I started by redrawing galactose in one of its chair forms. Let's go ahead and draw the other and compare which is going to be more stable. So the oxygen is still here, and this alcohol is still going up relative to the hydrogen. All you do when you change chair forms is switch all the positions from axial to equatorial and vice versa. So this methyl alcohol here is now equatorial where it was axial. This alcohol is still pointing up. It's going to be axial where it was equatorial. This alcohol is now going to be equatorial, kind of coming out this way. And this alcohol here is going to be pointed down in the equatorial position where it was axial here. And then finally, the last one is going to be equatorial, kind of following that positioning. I have not drawn this very well. Let's see if we can redraw that. I might have to just kind of draw it up. I know that's wrong. This is in the equatorial position, not the axial. And the axial is with the hydrogen going straight down. So ideally, you want this to be on the same plane as the bond that's opposite to it. So comparing these two isomers, which is more stable? Well, here we have 1, 2, 3, 4 groups axial, 1 equatorial. Here we have 1, 2, 3, 4 groups equatorial and 1 axial. So this is going to be the favored chair conformation because you have more groups in the equatorial position. Another way to say that is you have fewer groups in the axial position with unfavored 1,3 diaxial steric interactions. So this is going to be more favored. The next question asks us which sugar, glucose or galactose, is more stable, and explain. So in part 459, you were to draw glucose in its chair conformation, and it told you that glucose is highly stable. Therefore, all the groups in glucose were in the equatorial position. Well, here we have one group that is not in the equatorial position. Therefore, glucose should be more stable sugar than galactose. Draw a constitutional isomer. The constitutional isomer I'm going to draw is the open chair form, or the open form, not the chair form. And this is something you will get into in the sugars chapter, but I'm going to draw the Fisher projection. You may also see this in your biochemistry course if that is something you take. But this is indeed an isomer because if you look at the chair form, we have what we would call an acetal at this carbon. So it's, no, not that one. This carbon is an acetal. It's attached to 2 oxygens. It's a hemiacetal in this position. You'll get to that nomenclature. Don't worry about it too much now. But that can be opened into an aldehyde, which is an isomer. So let me finish this off quickly. I believe an OH on this side and a CH2 OH. This is an isomer of galactose. Another way you could draw this if you're not a fan of the Fisher projection or if you've never dealt with it before, I will draw the skeletal form. So OH, I'm not drawing stereochemistry because that would take a lot of thought. But it can be done. Alcohol in every carbon. So again, this is an isomer because we have the same amount of atoms, same number of carbons, hydrogens, and oxygen. But here we have an aldehyde where we had an ether in the closed chain form. The last question asks for you to draw a stereoisomer of galactose that is different from glucose. So I'm going to go ahead and any stereoisomer you choose would be fine. I will go ahead. I had drawn glucose, but let's just do a different one. OH up, OH down. And then maybe we do this one down. This one up. And this one up. Any way you draw it, as long as it's a different stereoisomer from this or glucose, is fine.